In this lesson, you're going to be dealing with optimization problems. These are typically word problems where we're going to be maximizing or minimizing a quantity. For example, let's say that you are a business. You may want to be interested in figuring out how many items should you sell so that you maximize your revenue. On the other hand, you may be interested in how many items should you produce so that you minimize cost. Other type of problems that appear in these discussions have to do with physics problems, problems that involve distance, time, and speed. And it's very typical, given a particular situation, to try to find out how to minimize the time that it takes a particular person to travel along a particular path, for example. The point is that in all of these problems, you're going to be maximizing or minimizing a particular quantity. In general, all of the problems involving optimization belong to two categories. For this reason, I will be guiding you through two examples that will demonstrate each category. You'll see exactly what I'm talking about when you go through example 1 and example 2. At the very end of the lesson, I will outline 4 steps that are pretty much always used in optimization problems. You know that when dealing with word problems, you cannot find a single method that works for all. However, there are some steps that are very consistent throughout, and there are 4 in particular that I want to outline at the end of this lesson. You're going to see that those 4 steps are going to be used in example 1 and example 2. There are going to be a few differences in the 2 examples because of the 2 different categories that I was talking about, but those 4 steps are going to be consistent in both examples. If you want, you can even skip towards the end of this lesson where I begin the discussion of those 4 steps so that you skim through them before you begin listening to example 1 and example 2. However, you don't have to. I'm going to guide you step by step, and then at the end, when we discuss the steps, you're going to really be able to appreciate them a bit more. Let's go ahead and tackle the first optimization problem. Let's read it together. A manufacturer needs to produce a cylindrical container with a capacity of 1,000 centimeters cube. So they're giving us volume here. And I know that because they mentioned the word capacity, and I can also see the units. The top and bottom of the container are made of material that costs 5 cents per square centimeter, while the side of the container is made of material costing 3 cents per square centimeters. Find the dimensions that will minimize the company's cost of producing the container. So here, we are dealing with a minimization problem. We are minimizing, and we are minimizing the cost to produce such cylindrical container. So what we need here is to be able to find a function that will represent the cost of this manufacturing company. Once we have the cost function, we will try to see exactly what are the dimensions that will minimize the cost for this company. So how do we start building the cost function? The first thing that we're going to go ahead and do is to break things up into the cost for producing, let's say, the top and the bottom, and then the cost for producing the sides of the cylinder. All right, so step number 1. Notice that here we don't have to have a let statement because the problem already chose the variables for us. Think about it that way. H is for the height and big R is for the radius of the cylinder. So we don't have to have a let statement. So number 1, let's do the cost of producing the top and the bottom. So the cost here is going to be, let's see, the top is made up of a circle the bottom is made up of an identical circle. So then that means that we have two circles. And the area of a circle is pi r squared. So then we're going to have 2 pi r squared. And then we will apply the cost to that, which we said that for the top and the bottom, it will be 5 cents. So times 0.05. And this is going to give us, once we multiply 2 and 0.05, we are going to get 0.1 pi r squared. So this is the cost of producing the top and the bottom. Now let's go ahead and find the cost of the side of the cylinder. Now the side of this cylinder, imagine that you actually open the cylinder up. The side will take on the shape of a rectangle. This length over here is just what used to be the height of the cylinder, so that will be h. And then this length over here is what used to be, when the cylinder was closed, the circumference of this circle over here, which is given by 2 pi r. So then the area of the rectangle, being base times height or length times width, will be 2 pi r times the height, which is right here in the bottom. So with that in mind, we can now go ahead and compute the cost of the side of the cylinder. That will just be 2 pi RH times, now applying the cost, 0.03. And then when I multiply the coefficients, the numerical coefficients, 2 times 0.03, we are going to get 0.06 pi r and then h. Now let's see here the total cost. The total cost will now be the cost of the top. Let me put it here, the top and the bottom, plus the cost of the side. So then that is going to give us very nicely 0.1 pi r squared plus 0.06 pi r h. Now, this is already looking like a very nice cost function. The only thing is that there are too many variables. I have big R and H. I would love to get rid of one of these variables so that I can have one single independent variable, something that plays the role of X, for instance. So with that then, in order to achieve that, why don't we use the volume? We haven't used the volume yet. We know that the volume of a cylinder is equal to the area of the base, which is, the base is a circle, so pi r squared times the height of the cylinder. The volume we know is 1,000, so we can set that equal to 1,000, and then we're going to have pi r squared times h. Now here, I think that it will be nice to solve for h. When we solve for h, we can take that expression and substitute it here into the cost. By substituting h with another expression, the only variable involved is going to be r. So now the cost will be in terms of r. Let me show you exactly what I have in mind. So if I solve for h, I will be dividing by pi r squared, both sides. So I am going to have that. That means that this will cancel here. And then we're going to have that h equals to 1,000 over pi r squared. Now I can take this expression and substitute it here into h. So then let me continue here with that substitution. We are going to have that the cost is going to be equal to 0.1 pi r squared plus 0.06 pi r, and now I am going to substitute 1,000 divided by pi r squared in place of h. So when we do that, look at this. Pi will cancel, this r will cancel, and this exponent is going to go to 1. So then we're going to end up getting 0.1 pi r squared plus 0.06 times 1,000. You know what? I know, let me just right away write 60 instead. 0.06 times 1,000 is just going to be 60. Divided by, in the denominator, we were only left with r. So now that I have this expression right here, this is a perfect candidate for my cost function. This becomes my cost function. And the function now is in terms of r. R is like x. It plays the role of x. So I can even write my function now in function notation. So the function becomes c of r equals 0.1 pi r squared plus 60 divided by r. I know that some of you are wondering why I decided to solve for h. Why not solve for r squared in the volume? The only reason why I chose h is because by choosing h, we just end up doing a simple substitution into this cost function. If I were to have solved for r instead, remember that what we had, let me do it here on the side, what we had was 1,000 equals pi r squared times h. Imagine that I would have solved for r instead. Then because I have r squared, in order to get rid of the exponent, I was going to have to consider the square root. So then that means that I was going to somehow have over here a radical involved, and I wanted to avoid radicals. So it was a lot easier instead to solve for h. Eventually, we're going to be looking for critical points. And whenever we look for critical points, in order to decide whether they are indeed valid critical points, we have to check them to see if they belong in the domain of the function. We have to see if the function is defined at those possible critical points. That really means that we should right now state the domain of our function. We should take care of the domain so that when it's time to find critical points, we can just quickly have a check. So what is the domain of this function right here? Well, here in the first term, I have 0.1 pi, but this is a coefficient, r squared. This is the variable r. That means that the first term is valid for every single r. Now, r must be positive here because we're talking about radius. So then I'm hoping that it is obvious that I am excluding negative values for r. It makes no sense to have a negative radius. So just immediately exclude negative r values. But now in the second term over here, r cannot be 0 because division by 0 is undefined. So then that means that the domain of this function consists only of positive r values. Any r value as long as it's positive. I'm going to make a note of that. And I'm going to write over here that the domain of my function c will consist of every number that is greater than 0, but not equal to 0. So from 0 all the way to positive infinity. And again, I am excluding negative numbers because r must be positive. So this becomes the domain of this function. Now then, remember that we want to be able to minimize the cost. That means that I would like to find the value of r where the cost will be at its minimum. Pretty much the value of r where the cost function is going to have an absolute minimum. That's what I want. I don't even want a local minimum. I want to find out an absolute minimum in this interval right here. So now in order to do that, we need to start looking for critical points. So in order to look for critical points, I need to find the derivative. In order to differentiate, I find it easier in this case to take 60 over r and rewrite it as 60 times r to the negative 1. And now differentiation becomes straightforward. So then differentiating, we are going to have here 2 times 0.1, that is going to be 0.2 pi, and then r minus 60 times r to the negative 2. And then this is going to give me 0.2 pi r minus 60 divided by r squared. And that becomes the derivative c prime of r. So this is what we get for that value. Now then, in order to find critical points, I have to consider two cases. Number one, where c prime of r is equal to 0, and two, where c prime of r is undefined. Okay. Now, it so happens that in my domain over here, look at the derivative. The derivative is always defined because the only issue here is if r is equal to 0, but 0 is being excluded. So then that means that this is never an issue. We're never going to have a critical point coming out of the derivative being undefined. The derivative is actually never undefined. So the critical points are going to come, hopefully, from finding the derivative and setting it equal to 0. All right, we already have the derivative, however. So I'm going to take that 0.2 pi r minus 60 over r squared, and I'm going to set it equal to 0. And now I am going to solve. So 0.2 pi r, I'm going to bring 60 over r squared to the other side. I'm going to put this over 1 and cross multiply. Continuing here, we're going to have 0.2 pi r cubed equals to 60, and r cubed is going to equal to 60 divided by 0.2 pi. So then now what we have to do is to take the cube root. So we're going to have the cube root of 60 divided by 0.2 pi. And when we do that, this will be approximately equal to 4.571 centimeters. Okay, so this is exactly what we get as a possible critical point. Let's quickly make sure that this is a valid critical point. For it to be a valid critical point, this value has to be in the domain of the original function right here. And look at the domain from 0 to positive infinity. 4.571 is beautifully in the domain of that function. So this is actually over here a valid critical point. Okay, and we only obtained one critical point. So if we are going to have an absolute minimum, it better happen at 4.571. So my next task now is to show that at this particular r value, the cost function is going to have an absolute minimum. Before we start the discussion on the absolute minimum, I have written down here some of the information that we already knew. We have our function c of r, which is equal to this expression here. We have the domain of c of r, and we found one critical point, which is 4.571. So there are two ways that we can now investigate the absolute minimum component. We can use the first derivative test or the second derivative test. I'm going to go ahead and begin with the first derivative test and show you how to do that. And then I'm going to show you how to arrive to the same conclusion of an absolute minimum with the second derivative test. And then at the end of the day, it's going to be your choice which method you will employ. So in this case, if I'm going to use the first derivative test, what I really need is indeed the first derivative, but we already did that. We know that the first derivative here is equal to 0.2 pi times r minus 60 times r to the negative 2. And I will take a little bit of time here and re-express this as 0.2 r minus 60 divided by r squared. So this is the first derivative right here. And then for the first derivative test, we will now transition to the number line analysis. So the way that I like to do that is to draw the number line right here. And then I'm going to put here a reminder that this is going to be the analysis of the first derivative. And then we're going to go ahead and write down the actual function for the first derivative, 0.2 pi r minus 60 over r squared. Then on the actual number line, we are going to begin by marking down the position of 0. I'm going to put a parenthesis to indicate that we are not including 0. And then towards the right, I'm going to write down the critical value, 4.571. And then I'm going to put a heavy dot over here indicating that at this value, the first derivative was actually equal to 0. And then what I want to do is to now investigate the sign of the first derivative in this interval and also in this interval. And all that I have to do is to choose a test point. For example, any number between 0 and 4.571, the easiest one that comes to mind. So in this case, 1. Look at this. If I plug in 1 for r in the first derivative and 1 here, I am going to get, let me do that here just informally. I'm going to have 0.2 pi times 1, which is just 0.2 pi, minus 60. I don't even need a calculator for that. I know that 0.2 pi minus 60 will be negative. So then I know that the first derivative is going to be negative in this interval. I'm going to put little negative signs to remind me of that. Then let me go ahead now and choose a test point in this interval here. Something like 10. 10 is a very easy number to work with. It's going to eliminate a lot of the decimals that you see right here. So then let's do that. We are going to have 0.2 pi times 10 minus 60 divided by 10 squared, and 10 squared is going to be 100. So then this is going to give me 2 pi minus 60 over 100, or 6 over 10. If you simplify, that is just going to give me 0.6. And I can stop right here. Immediately, I know that 2 pi is bigger than 0.6. So this difference is going to end up being a positive difference. So I'm going to go ahead and put plus, plus, and I don't need another test point. One test point in each interval between the critical points is enough to determine the sign of the first derivative in the entire interval. So I know that in this entire interval, the first derivative is negative. And in this entire interval right here, the first derivative is always going to be positive. So then at the critical point, what I really have right here, it's a local minimum. So I have something like this. I have a local minimum at the critical point. Now let's think about it. Is this a local minimum or an absolute minimum? And the way that you're going to reason through that is by noticing that in this first interval right here between 0 and 4.571, the derivative is always less than 0. And what that means is that the graph is always decreasing. So this is why I drew this little valley. The derivative is always decreasing in that interval. In this other interval right here, to the right of the critical point, if you notice, the derivative is positive. Then that really means that the graph here is increasing, and the derivative will never change again. In other words, to the right of the critical point, the derivative will continue being positive for any value of r. So then that really means that in this interval right here, the graph will continue increasing forever. Let's go on the other side right here. From 0 to the critical point, we said the graph is always decreasing. So always decreasing here, always increasing here. So then that means that at the critical point, we don't just have a local minimum. We actually have an absolute minimum because the graph will never change direction again. Never. And we can see that again repeating myself because the derivative will be forever positive in this direction and forever negative in this direction. So the graph is always going to be increasing in this interval, and the graph will always be decreasing on this interval to the left of the critical point. That really means that at the critical point, the graph is going to achieve its absolute minimum. That is going to happen when R is precisely 4.571 centimeters. So it is there for this particular R that the cost is going to be minimized at the absolute minimum. If we want to use the second derivative to arrive to the same conclusion that at the critical point we have an absolute minimum, what we are going to do is to find the second derivative. So the second derivative will be equal to 0.2 pi plus 120 times r to the negative 3. Turning now the negative exponent positive, the second derivative of c is going to be equal to 0.2 pi plus 120 divided by r to the third. So according to the second derivative test, we're going to now take the critical point, this value right here, 4.571, and we're going to substitute it in the second derivative, and we're going to look at the sign. So then substituting c double prime of 4.571 will be equal to 0.2 pi plus 120 over 4.571 to the third. And when you get your calculator and you simplify this, you're going to end up getting that this is approximately equal to 1.885. And notice that 1.885 is a positive number. So this is a positive number right here. And according to the second derivative test, if the second derivative at the critical point is positive, then that means that at 4.571, what we really have is a local minimum. If we get a positive value for the second derivative, that means a local minimum at that critical point. But what we want is to somehow argue for absolute minimum, not a local minimum. So then what we are going to do here is to maybe, why not analyze the function at positive infinity and the function as we approach 0 from the right. So I'm going to consider one case, and this is about limits. Let's look at the limit as r approaches positive infinity of the cost function, the original function. I want to see the end behavior of the graph at positive infinity. So this will be the limit as r approaches positive infinity, and the function is 0.1 pi r squared plus 60 divided by r. And what I want you to notice is the following. As r gets very, very large, because r goes to positive infinity, the first term has r squared. So then this term over here is going to go to positive infinity. So I'm going to have, in the first case, that the limit of the first term is going to go towards positive infinity. Now let's see what happens with 60 over r. As r gets very, very large, the denominator is getting very, very large, the entire fraction then is going to go to 0. So then I'm going to have over here plus 0. Well, infinity plus 0 is not an indeterminate form. This is just positive infinity overall. So then what we really get is that if you were to sketch this function, it is not my intention to do that. So I'm just going to symbolically draw a rough sketch over here. This is C of r. What I have is that the end behavior of this function pretty much goes towards positive infinity in that direction. Remember that the critical point, let's say, is going to be somewhere here, 4.571. Now I want to see the behavior of the graph as r approaches 0 from the right. So this will be the second limit that I will analyze. The limit as r approaches 0 from the right of C of r. This is going to be equal to the limit as r approaches 0 from the right of 0.1 pi r squared plus 60 divided by r. Let's see what happens. If r is approaching 0 from the right, the first term, because it has r squared, is going to approach 0. So this term is going to go to 0 pretty much. So then I'm going to write just that, 0 over here, plus. Now, what happens with the second term? 60 is fixed, but r is getting very, very small. So 60 over something that is getting very, very small is going to be something very, very large. So that is going to go to infinity. And again, I get infinity. So then what I have is that my graph will keep approaching the y-axis asymptotically. It's going to go to infinity. So then to recap, as r goes to positive infinity, the graph is going to die off by going towards positive infinity. And as r approaches 0 from the right, the graph continues going to positive infinity. And when r is equal to 4.571 at the critical point, we already know that we have a local minimum. But how do we argue that we have more than that at the critical point, that the graph actually achieves its absolute minimum there? The way that you're going to realize that this is the case, that we have an absolute minimum there, is by again remembering that when r goes to positive infinity, the graph goes on to positive infinity forever. And as r is approaching 0 from the right, the graph again goes off to positive infinity. So positive infinity forever here, positive infinity forever here. So then, if we are going to have another value for r, something different from this one, imagine another value of r where the graph is going to have an absolute minimum, then that's going to happen at a mountain or a valley. So then that means at a critical point. However, we only got one critical point. We don't have another critical point. We only found one, this one right here, 4.571. So then that really tells us that not only will the graph have a local minimum at this value of r, but it's going to have more than that. It's going to have an absolute minimum at 4.571, which is then telling us that if the company wants to minimize its cost, it should then let r equal to 4.571 centimeters. So at this particular value of r, the cost is going to be at its absolute minimum. Example 2 is another optimization problem, but now this problem is operating on a closed interval. And you're going to see exactly what I mean by that. In the previous one, we were doing an optimization problem where the domain of the function was pretty much open. It was infinite. Here, the domain of the function is going to end up being a closed interval. So then in order to maximize or minimize our function, we are going to use the extreme value theorem. We're not going to use the first derivative or the second derivative. All right, so let's read the problem together. Your task is to build a road joining a ranch to a highway that enables drivers to reach the city in the shortest time. So here is the road. If you go to the diagram right here, you can see the road right here. So this is the road that we're talking about. And right here, this is the highway. How should this be done if the speed limit is 60 kilometers per hour on the road and 110 kilometers per hour on the highway? So that means that we have the speed of the road that you can actually travel on the road and the speed that we can travel on the highway. The perpendicular distance from the ranch to the highway is 30 kilometers. So you can see it right here, the perpendicular distance. And the city is 50 kilometers down the highway. So from here to here is exactly what we have, 50 kilometers distance. What we are going to do at the moment is to perhaps let this distance right here, the distance from the right angle to where the road is going to touch the highway, let's call it X for now. So this is going to be X right here. This distance right here, that's going to be X. And I'm going to have a let statement for that. I am going to say to let X be that distance. And you know what? To make it easy, why don't we assign letters? Let's call this point over here where the 90-degree angle is, let's call it A. And let's call this other point right here where the road touches the highway, let's call it B. So going back here, let X be the distance between, let's say, between point A and point B. All right, so that's introducing X. So what I want to do here is to pretty much find a function for time, because what we want is the question, if you notice, is how should this be done if this is the speed on the highway? And what we want to do is to pretty much minimize time right here. You see, the shortest time. So why don't we somehow build a function for time, and then we're going to try to minimize that function. We're going to try to find the value of X that will minimize time for us. So again, we're building a function for time. So let's break this up into two components. Let's talk about, try to find the time that it will take to travel around along the road, given that we know the speed on the road, and then the time that it will take to travel along the highway, because we also know the speed. Then we're going to join the two together, and that is going to be our time function. And then we're going to try to minimize it so that we find the best possible combination. But in order to do that, why don't we first find the distance traveled along the road? And I can do that by using the Pythagorean theorem. So let's call this distance over here little d. And let's find little d. We know that x squared plus 30 squared is going to be equal to d squared. So then that means that d is going to be the square root of x squared plus 30 squared, which is just 900. And I don't say plus or minus because your distance is positive. So I'm going to write here that this is equal to the square root of x squared plus 900. So now then, the time along the road, let me call this t sub road, let me just write road, that is going to be equal, time is equal to distance divided by the speed. So then the distance traveled along the road, which is x squared plus 900 divided by the speed. And the speed on the road was 60 kilometers per hour. Then we're going to go ahead and build the time that it takes to travel along the highway. Let me just write high for highway. So the distance traveled along the highway, let's think about it. The distance that we're looking at is this distance right here. I'm going to be using green. That distance is going to be 50 minus x. So this is the distance that it takes to travel along the highway. That means that the time will be 50 distance divided by the speed, and the speed along the highway is 110 kilometers per hour. So now I can build the total time that it will take. So the total time, and that's going to be in terms of x. I will even use function notation. The total time will be the time along the road plus the time along the highway. That is going to be the square root of x squared plus 900 over 60 plus 50 minus x divided by 110. And that becomes our time function. Now, what I want us to do is to determine the domain of this function. This is something that should be done right away. As soon as you find your function, the function that you're going to maximize or minimize, you want to state the domain before you differentiate or anything like that. So what is the domain of this function? Look at this. The domain of the function completely depends on x. Now here in this radical, x is being squared and we're adding 900. So I can put any x over here and the radical is pretty much safe. Now let's look at this component, 50 minus x. Why don't we go to the diagram right here? Look at this. X could be 0. I mean, if x is 0, that means that this road becomes this perpendicular distance right here. So this becomes the road pretty much. That means that we're going to be going straight down to the highway and then boom, all the way here, 50 kilometers to the city. So x could be 0 or x could go as high as 50. If x is equal to 50, then that means that the road extends all the way to the city. So we would only be traveling along the road and we will be in the city right away. So x can vary. It can go from 0 all the way to 50. So those are the options that we have for x. That really means that will be the domain of my function. So I'm going to say here that the domain of my t of x function, of my time function, is going to be the closed interval from 0 all the way to 50. Now I want you to notice that my function t of x is continuous in this domain. There are no variables in the denominators. We only have 60 and 110. The variables are on top. And then inside of the radical, x squared plus 900 is always positive, no matter what x is equal to. And over here, 50 minus x, well, x is going to go as far as 50. Then that means that 50 minus x goes all the way from 0 to 50 as well. So there's nothing of a problem within these two terms as x ranges from 0 to 50. So t of x is beautifully continuous in its domain. And I'm going to make a note of that. So I'm going to say here that t of x is continuous in the closed interval 0 to 50 and differentiable. It is differentiable in the open interval, from 0 to 50. So we have continuity and differentiability in the interval 0 to 50. That really means that there exists an absolute minimum and an absolute maximum in this closed interval over here. So then I can use the extreme value theorem to determine the location of the absolute minimum or the absolute maximum. I already know it exists. And according to the extreme value theorem, the absolute max or the absolute min is going to exist at the end points, so at 0 and 50, or at the critical points. So let's go ahead and find the critical points. To do that, we're going to differentiate. So let me write over here, critical points. This is our goal right now. So to differentiate, I find it easier to turn the radical to exponent form, rewrite it as x squared plus 900 to the 1/2 over 60, and then plus 50 minus x divided by 110. And now finding the first derivative. So finding the first derivative, this is going to be equal to 1/2 times x squared plus 900 to the negative 1/2. Then using chain rule, this will be 2x, all this divided by 60. Then over here, plus the derivative of 50 is 0, and the derivative of negative x, so that's going to just be here -1 divided by 110. So this is what we have. And whenever you actually start simplifying things, notice how I can cancel these 2 with this 2 over here. I am going to rewrite this as x. X is going to stay in the numerator, but now in the denominator, I'm going to have 60, and I am going to have my radical, x squared plus 900. And then over here, minus 1 over 110. If you're wondering how did the radical go down, see here in the numerator, the exponent was negative 1/2. If I want to turn the exponent positive, then I bring this entire quantity down. And now when it becomes down, the negative 1/2 turns into a positive 1/2 as the exponent. And having an exponent of positive 1/2 is equivalent to having the square root of x squared plus 900. So this is how I got that expression, and this becomes the expression for the first derivative. So what I'm going to do now is to find my critical points by setting the first derivative equal to 0, or by seeing also where the first derivative may be undefined. Here I have the expression for the first derivative, and this is the domain of the actual function. So now to find the critical points, as I just said a few minutes ago, I want you to remember that in order for that to happen, we're looking for 2 possibilities, where the first derivative is equal to 0 and where the first derivative may be undefined. If you go back to the actual expression here of the first derivative, you're going to notice that there isn't a single value of x that will make the first derivative undefined. In the denominator, we do have an x term, but we have the square root of 900 plus x squared. In other words, notice over here is that the expression inside of the radical 900 plus x squared is never equal to 0. Never equal to 0. Now, if you don't notice that, what would happen if you do try to solve this equation? Imagine that you set it equal to 0 and you try to solve for x. You're going to get that x squared is equal to -900. And right there, you can practically stop. Notice how this statement doesn't make any sense mathematically, because you can never square a number and get a negative answer in return. So this over here has no solution. So this is impossible. That means that the first derivative, t prime, is defined for all values of x in the domain of the function. That means that if we're going to have critical points, it's going to come from part A, by setting the derivative equal to 0 and trying to solve. Let's go ahead and do that. So going from here, we're going to take the first derivative, which is x divided by 60 square root of 900 plus x squared minus 1 over 110, and we're going to set that equal to 0. And then I am going to solve by bringing this term to the other side and then cross multiply. In other words, x divided by 60 times the square root of 900 plus x squared, that will be equal to 1 over 110. Now, cross multiplication allows me to end up with the following equation: 110x equals to 60 divided by 900 plus x squared. Then I'm thinking that we can divide both sides by 60. 60s will cancel here. And then this 0 right here will cancel with that 0. And that's going to leave me with 11 over 6x equals to the square root of 900 plus x squared. In order to continue, I'm going to go ahead and square both sides of the equation. And the reason for doing this is because I want to get rid of the radical. That means that we're going to have 121 divided by 36, x squared on the left side. And then on the other side, we're just going to have 900 plus x squared. Then I'm going to bring this term right here, the x squared term, together to the left so that I can start simplifying like terms and then hopefully completely isolate the variable. In other words, continuing here, this will be equal to 121 over 36 x squared minus x squared equals to 900. And then getting a common denominator, this will be over here 36. Then in the numerator, I'm going to have 121 x squared minus 36 x squared equals to 900. Then 121 minus 36 is going to give us 85 x squared divided by 36 equals to 900. And then in order to continue solving, I'm going to get rid of 36 by multiplying both sides of my equation by 36. They will cancel nicely. And I am going to have 85 x squared equals to 900 times 36. That's going to be 32,400. Then we will divide both sides by 85. 85s will cancel on the left, and we're going to have that x squared is going to be equal to 32,400 over 85. So x will be equal to the square root of 32,400 over 85. When you simplify this with your calculator, this will be approximately equal to 19.524, and then the units are going to be in kilometers because x was measuring distance. Now that we have found critical points and all of that, it is time to figure out the value of x where the function t of x is going to have an absolute minimum. I am not going to use the first derivative test or the second derivative test to do that because I have a function that operates in a closed interval from 0 to 50. And on top of that, this function is continuous in this closed interval. So then I know that this function is going to have an absolute minimum and an absolute maximum here in this closed interval. And for that, I have the extreme value theorem that tells me exactly where to look for those values. If you remember, here I have very briefly, I have stated the extreme value theorem. The conditions of this theorem are that the function has to be continuous in the closed interval 0 to 50, which I have that if you look at the function above. And my function has to be differentiable in the open interval 0 to 50. Again, we don't analyze differentiability at the endpoints, only what happens inside of the interval. So I have continuity and I have differentiability. Then the conclusion of the theorem is that the absolute maximum or the absolute minimum is going to occur at the endpoints and or at the critical points, all of which I have. I have the endpoints and I found one critical point. So I know that my absolute minimum is going to happen at the endpoints or at the critical point. I don't care about the absolute maximum. I am minimizing the function, so I want the absolute minimum. That means that we're going to go ahead and right away try to compute t of 0, t of 50, and then we will compute t of the critical point. If you remember, the critical point was 19.524. And in order to compute these values, we're going to take 0, 50, and 19.524, and we're going to substitute those x values here into this function right there. And you can perfectly use your calculator for that. Now, 0 is so simple. I'm just going to quickly do this here. This will be the square root of 900, because if x is 0, x squared is 0, divided by 600 plus 50 divided by 110. That is going to be approximately equal to 0.955. Then t of 50, same idea. If you just plug in 50 into the function, you're going to have 900 plus 50 squared plus 50 minus 50 divided by 110, and here on the left divided by 60. So then this will be approximately equal to 0.97183. And when you plug in 19.524, we're going to have 900 plus 19.524 squared. That will be divided by 60 plus 50 minus 19.524 divided by 110. That will be approximately equal to 0.874. Now you're going to look at all of the three answers that we got: 0.955, 0.97183, and 0.874. So then it is clear that this value right here, this one right here, is the smallest value of the function. So then this is telling us that the absolute minimum is going to happen exactly at the critical point. That means that x should be 19.524 as the distance between point A and B. And just in case we forgot about that, here I have that diagram again, and you can now see that x was representing this distance right here, the distance between A and B. That really means that this distance right here that I'm highlighting in blue, that distance should be 19.524. And that implies that this distance between point B and the city right here should be 50 minus 19.524. So right here, I'm going to make a note of that. 50 minus 19.524 with your calculator, that will become about 30.476 kilometers. So then in order to build a road and to minimize the time of travel, the optimal way of doing that is to build a road in such a way that the distance between A and B is precisely 19.524 kilometers, and then to run along the highway for a distance of 30.476 kilometers. This will be the best way to minimize time. I have put together here a few steps that you can always follow when doing optimization problems. And once we discuss these steps, you're going to realize that this is exactly what I did in both examples. However, I just want to let you know that, and you probably know this, every word problem is different, and there will always be something slightly different from the previous one or the last two examples that you did or so forth. So always expect something new in every word problem. But for the most part, I will talk about the 4 steps that are pretty much consistent in every optimization problem. Number 1, make sure that you read the problem carefully. Identify the variables that are playing a role. In example 1, if you remember with the cylinder that we had big R for the radius, we had little h for the height of the cylinder. In example 2, we were talking about little x, which was the distance between points A and B, and so forth. So make sure that you identify your variables and that you assign symbols, just like big R, little h, little x. In step number 2, draw a diagram almost right away. In fact, drawing a diagram can even be part of step 1, if it's not given to you, of course. If you have a diagram, fantastic. You may just have to fill in the gaps. And then once you have your diagram and your pictures, make sure that you start identifying the relationship between your variables. If it's about area, what is the formula for the area? How are these variables related through area or through volume or through the Pythagorean theorem? So little relationships like this. And then that will take you on to step 3, which is now deriving the actual function that you're going to use. So that's what I mean over here. What is now the function that you're going to maximize or minimize? If you remember in example 1, it was about minimizing cost. So we had a cost function. In example 2, it was about minimizing time. So we had a time function. And then as soon as you build the function that you will maximize or minimize, make sure that you state the domain right away. Sometimes the domain is going to be infinite, so open. Sometimes the domain is going to be closed. That means that you're going to be including the endpoints. If the domain that you have determined for your function is open, you're going to be using the first derivative test or the second derivative test to locate the places where the function is going to have an absolute max or an absolute minimum. And you saw that entire process with example 1. If the domain of your function is a closed interval, you're going to be using the extreme value theorem to find the locations of the absolute max or the absolute min. And this was shown in example 2. Only that whenever you use the extreme value theorem, like any other theorem in calculus, you want to make sure that your function satisfies the conditions of the theorem. If it's differentiability in the domain, show that briefly or just mention that. If it's continuity, do the same thing. And once this is done, then your next step is to find the critical points. This is something that you're going to do all the time, whether you use the first and second derivative test or whether you use the extreme value theorem to locate the absolute maximum or the absolute minimum. You will need to find the critical points. You know that the critical points happen where that derivative is equal to 0 and or the derivative is undefined. And once that is done, then you proceed with the first derivative test or the second derivative test or the extreme value theorem.